In mathematics, relative position is the concept of the position of one object relative to another. In this video, we will be discussing measures of relative position in mathematics in the modern world. We will cover 5 major topics: Z-scores, percentile, quartiles, box-and-whisker plots, and stem and leaf diagram. My name is John Mark de Lima, and this presentation is our final group output and would be submitted to Mr. Antonio Jr. Fajardo, General Education 3 Mathematics in the Modern World instructor. Without further ado, let's begin. Let's start with the Z-scores that would be explained by Mark Joven Gregorio.
Z-scores. A Z-score is a numerical measurement of how many standard deviation an entity is from the mean. A Z-scores describe the position of a row score in terms of its distance from the mean when measured in standard deviation units. The Z-score is positive if the value lies above the mean and negative if it lies standardized below the mean. It is also known as a standard score because it allows comparing scores on different variables by standardizing the distribution. A standard normal distribution (SND) is a normally shaped distribution with a mean of 0 and a standard deviation SD of 1. It is useful to standardize the values row scores of a normal distribution by converting them into Z-scores because it allows researchers to calculate the probability of a score occurring within a standard normal distribution, B, and enable us to compare two scores that are from different samples which may have different means and standard deviations.
How to calculate Z-scores. The formula for calculating a Z-score is Z is equal to X minus mu divided by sigma, where X is the raw score, mu is the population mean, and sigma is the population standard deviation. So as you can see in the formula, Z is equal to X minus X divided by S, where Z is the standard score, S is the standard deviation of a sample, X is each value in the dataset, and X with line above is mean of all values in the dataset. For example, you take SAT and score 1,100. The mean score for the SAT is 1,026 and the standard deviation is 209. How well did you score on the test compared to the average test taker? So that's the question. So our step 1 is write your x value into the z-score equation. So which means that we should substitute the variables based on the formula so that we can calculate it. So step 2, put the mean mu into the z-score equation. Step 3, write the standard deviation sigma into the z-score equation. And then step 4, calculate. So 1,100 minus 1,026 divided by 209 is equal to 0.354. This means that your score was 0.354 as the devs above the mean. And now, let's take a look at number 2, percentile. So percentile is a term that describes how a score compares to other scores from the same set. So as you can see on the image, it is the 70th percentile among the set. So numerical data can be sorted in increasing or decreasing order. Thus, the values of a numerical data set have a rank order. A percentile is the value at a particular rank. For example, if your score on a test is on the 95th percentile, a common interpretation is that only 5% of the scores were higher than yours. So the median is the 50th percentile. It is commonly assumed that 50% the values in the dataset are above the median. And percentiles are frequently used to understand test scores and biometric measurement. How to calculate percentile? Percentiles can be calculated using the formula n is equal to p divided by 100 times n, where p is equal to percentile, n is number of values in a dataset, sorted from smallest to largest, and n is equal to ordinal rank of a given value. Let's take a look at this example. Let us consider the percentile example problem. In a college, a list of grades of 15 students have been declared. Their grades are 85, 34, 42, 51, 84, 86, 78, 85, 87, 69, 74, and 65. Find the 60th, 80th percentile. So we need to find the 80th percentile. So our solution is step 1, arrange the data in the ascending order. So as you can see, it was arranged in an ascending order. Step 2, find the rank. So to find the rank, we have to divide the percentile by 100. So our rank is 0.8. Step 3, find the 80th percentile. So the 80th percentile is equal to 0.8 times 12 is equal to 9.6. Since it is not a whole number, round to the nearest whole number. Therefore, 9.6 is rounded to 10. Now count the values in the given dataset from left to right until you reach the number 10. From the given dataset, 10th number is 85. Hence, 80th percentile of given dataset is equal to 85. So let's move on and hear Jamie Lagatic explaining the third topic, which is quartile.
Quartile are three values that split sorted data in four parts, each with unequal numbers of observation. The quartiles data into 3 points, a lower quartile, median, and upper quartile, to form four groups of the data sets. Along with the minimum and maximum values of the data set, the quartile divide a set of observations into four sections, each representing 25% of the observations. The quartiles are used to calculate the interquartile range, which is a measure of variability around the median. To understand the quartile, it is important to understand the median as a measure of central tendency. Example: 1, 3, 3, 4, 5, 6, 6, 7, 8, and 8. The numbers are already in order. Cut the list into quarters. In this case, quartile 2 is halfway between 5 and 6. Q2 is equals to 5 plus 6 divided by 2 equals 5.5. And the results is quartile 1 equals to 3, quartile 2 is equals to 5.5, and quartile 3 is equals to 7.
And that's how we calculate quartile and how to use it. Let's take a look at our fourth topic, which is Box-and-Whisker plot by Ivan Gonzalvo.
Box-and-Whisker plot, a graphical method of displaying variation in a set of data. And this is the diagram and the arrow. Upper is 5, 10, 16, and the upper is 18, 20, 32. Upper extreme is 32, lower extreme is 5, median is 17, upper quartile is 20, lower quartile is 10. Box-and-Whisker plot. The box-whisker plot, sometimes simply called the box plot, is a type of graph that helps visualize the 5 numbers summary. A box plot is ideal for comparing distributions because the century spread and overall range are immediately apparent. Figure 4, 5, 2, and 1 shows how to build the box-and-whisker plot from the 5 number summary. Figure 4, 5, 2, and 1 building a box-and-whisker plot. This is a box, and the left side is we have whisker, minimum, lower quartile, quartile 1. In the middle is we have median, quartile 2. And the right side is we have whisker, maximum, upper quartile, and quartile 3. Sample of box-and-whisker plots. Find Q1, Q2, and Q3 for the following dataset and draw a box-and-whisker plot. 2, 6, 7, 8, 8, 11, 12, 13, 14, 15, 22, 23. There are 12 data points. The middle two are 11 and 12. So the median quartile 2 is 11, 5. The lower half of dataset is the set 2, 6, 7, 8, 8, 11. The median here is 7, 5. So quartile 1 is equal to 7.5. The upper half of the data set is the set 12, 13, 14, 15, 22, and 23. The median here is 14.5, so quartile 3 is equal to 14.5. A box and the whisker plot displays the values quartile 1, quartile 2, and quartile 3, along with the extreme values of the dataset, 22 and 23 in this case. And this is the box and the arrow.
And for the fifth and last topic, stem and leaf diagram, to be discussed by Princess Carmi Copiado.
Stem and leaf diagram. A special table where each data value is split into stem, the first digit or digits, and a leaf, usually the last digit. A stem and leaf diagram is a method of organizing numerical data based on the first place value of the numbers. Each number is split into two parts. The first digits forms the stem. The last digits forms the leaf. The leaf should only ever contain a single digit. For example, the number 154 would be split into two parts, where the digits 15 would be the stem and 4 would be the leaf. Note: a stem and leaf diagram must have a key, something referred to as a legend. This explains how to convert the digits in the stem and leaf diagram into a single data point. Remember to include any units in the key if appropriate. Dual stem and leaf diagram. Comparing datasets is simplified by using a dual stem and leaf diagram which have two sets of data represented back to back. For example, here are two sets of data showing test scores of 2020 males and 2020 females. By combining them together to form one dual stem and leaf diagram, we can directly compare the two sets of data.
So let's recall what we've discussed in this video. So number 1, we discussed Z-scores. It is the values relationship to the mean of a group of values. Number 2, percentile, expressed as the percentage of values. We also discussed quartiles. It is the values that divides a list of numbers into quarters. And number 4, box and whisker plots. It is a graphical method of displaying variation in a set of data. And lastly, we've discussed stem and leaf diagrams. And plus dual stem and leaf diagram, which is the data is broken down into stem and a leaf, thus the name. And that would be all. Thank you for learning with us. And always remember, every day we are still learning. Goodbye.